Good day, everyone. I am Veronique, and I am going to present the unsteady hydromagnetic coated flow under an oscillating pressure gradient and uniform suction and injection. This study was done, Mr. Victor Job, under the supervision of Dr. Rao. So the study of unsteady coated flow under varying different physical effects has been studied extensively in the last few decades in areas such as the petroleum industry and the purification of crude oil. Hydromagnetics, also known as magnetohydrodynamics, focuses on the dynamics of magnetic fields in electrically conducting fluids, such as in liquid metals and plasma. It combines the principles of both fluid dynamics and electromagnetism. Suction or injection on the boundary contributes significantly in the field of aerodynamics and the space sciences, and its main purpose is to influence the flow of fluid in the channel. Coated fluid flow have been examined in a number of different ways, such as experimentation, finite difference method, permutation technique, and the finite element method. This method is powerful and an effective numerical method, which is applied to the real-world problems such as heat transfer, solid and fluid mechanics, and electrostatic. When we are applying this method, the domain given is viewed as a collection of subdomains, and over each subdomain, the governing equation is approximated using any of the traditional variational methods. These methods, Petrov-Galerkin, least squares method, Rayleigh-Ritz method, and the Galerkin Finite Element Method, which would be used in this study. Our objectives are: 1, to investigate the unsteady hydromagnetic coated flow under an oscillating pressure gradient and uniform suction and injection, and 2, to examine the effect of suction, Hartmann number, Reynolds number, amplitude of the pressure gradient, and the frequency of oscillation on the velocity of the fluid. Our problem has 2 infinitely long horizontal parallel plates. The lower plate is stationary while the upper plate moves with a constant velocity u0. The fluid flows with uniform injection through the lower plate and uniform suction through the upper plate. The fluid which flows between the 2 plates are influenced by an oscillating pressure gradient, del P del X, in the X direction. At t equal to 0, a uniform suction from above and injection from below are applied. Also, a uniform applied constant magnetic field, B0, is applied to the whole system. For the problem, we have the following governing equations for fluid flow and its initial conditions and boundary conditions as shown. These governing equations, initial conditions, and boundary conditions are transformed in dimensionless form by these non-dimensional variables shown. In addition to that, we have our suction parameter, Hartmann parameter, and Reynolds number. After these variables are applied, we get the following non-dimensional equation with the non-dimensional pressure gradient applied and our dimensionless amplitude and frequency of oscillation of the pressure gradient. We also have our dimensionless initial and boundary conditions as follows. The numerical solution of the problem is solved using the Galerkin Finite Element Method under the initial and boundary conditions to determine the velocity distributions. And according to this method, a spatial semi-discretization of the problem was performed such that the associated trial and test function spaces are equal. and the finite element approximation is represented using Lagrange's basis function. Together with this, we use the Crank-Nicholson scheme and apply that to obtain the system of linear equations, which is solved using MATLAB. Our results. So figure 2 shows the time development of the velocity of u. Here, we can see for various values of t, as time increases, our velocity also increases. So, the flow velocity approaches a steady state with increasing t. Figure 3 shows the effect of varying Hartmann number and the suction on the time variation of u. The first diagram shows the effect of the varying Hartmann number. Here, as the Hartmann number increases, our velocity decreases. This occurs due to the magnetic damping force on velocity u increasing. The second diagram shows the effect of the varying suction parameter. Here, as the suction increases, velocity decreases. This is because of a fluid convection from areas in the lower half of the channel to center, in which speed of the fluid is higher. For both figures 2 and 3, these results are in agreement with the results obtained by Hazem Attia in his study of unsteady hydromagnetic coated flow with heat transfer in the presence of uniform suction and injection. Figure 4 shows the effect of varying Reynolds number and amplitude of the pressure gradient and time variation of u. The first diagram shows the effect of varying Reynolds number, and as the Reynolds number increases, the velocity also increases. The second diagram shows effect of varying amplitude of the pressure gradient. Here, we have the frequency of oscillation being equal to 0. And as the amplitude of the pressure gradient increases, velocity also increases. Figure 5 continues to show the effect of varying amplitude of the pressure gradient on time variation of u. In the first diagram, our frequency of oscillation is now 1, and our time is now 1.85. For effect of varying amplitude of the pressure gradient, as those values increases, our velocity also increases. Here, it increases faster than when the frequency of oscillation is equal to 0. Our second diagram shows when the frequency of oscillation is increased to 5. Here, our amplitude of the pressure gradient, as it increases, our velocity continues to also increase. Here, our oscillation is faster, giving free flow at the amplitude of pressure gradient when it's equal to 0. Figure 6 shows the effect of varying of frequency of oscillation on time variation of u. Here, as our frequency of oscillation increases, our velocity decreases. Therefore, pressure is decreasing as the frequency of oscillation increases. Our conclusion: it was revealed that the suction parameter, Hartmann number and Reynolds number has a marked effect on velocity. Here, the amplitude of the pressure gradient and various values of the frequency of oscillation, it was found that velocity increases as these values increases. Also, as the frequency of oscillation increases, the velocity decreases. These are our references. And that concludes our presentation. If you have any questions, you may send an email to the following link, and we'll be happy to assist. I thank you.